We will now be doing Physics 2, the exam 2, which was taken in 2009, right? So like 10 years ago. And we have a bar magnet that is being dropped from above, and it falls through a loop of wire. Now we have to find out which statement is true, right? Which one is correct. Well, over here I'm just going to draw my bar magnet right here. And actually I'm going to put it a little lower because the picture is quite large, right? So over here, we're going to say that this is going to be our south pole, and this is going to be our north pole. Well, it's important for you to know this may be an exam question, conceptually. But whenever you have a bar magnet, the north pole is going to have field lines coming out of it, like this, okay? So there's a field line coming out, and it's going to go back inwards towards the south pole, and from the south pole it's going to go to the north pole. So you have a lot of field lines doing this, okay? That's what a bar magnet does. Now these lines, they never intersect, they never cross, they're always, you know, they're never perpendicular, they never cross, all right? They never intersect, they're always parallel to each other. So that's another exam question. As you can see, the north pole always has lines coming out of it, coming out, and the south pole always absorbs the field lines, right? So now, using what you know, you can technically solve this problem, kind of. So let's draw it out again, right here. We have a bar magnet. Let's draw our loop right there, and we're gonna have our magnet right here. Okay, cool. So that's our magnet. Over here is gonna be the south pole, and over here is gonna be the north pole, right? So notice something that, well, let's actually draw it like this. South and north. Alright, so notice that we are falling down, so our velocity is going to be downwards. Our velocity is going to be downwards. That means that we have field lines coming this way. That's our field line. If you want to see it like this, you can see it. It's the same thing. We just have a bunch of field lines coming outwards. Now, as we move the bar magnet closer to the ring, you're going to be increasing the amount of field lines, which are these guys, which are over here. Let's do it right there. You're going to be increasing the amount of field lines. Now, if you increase the field lines in the ring, you're going to be creating a new magnetic field. And the magnetic field is just called a B field. Okay, and so that's called a B field. Now, we have to find which way the current is going to flow in this new B field that you're creating. Well, it's important for you to know that whenever you increase the B field, your induced B field, let's call that B induced, is going to be in the opposite direction for where you came from, okay? So it's going to be in the opposite direction. Well, let's see. You have a lot of field lines coming down this ring, so you're going to be increasing the B field, all right? So the more lines you have passing through this ring, the more B field you're going to have, the more of an increase you're going to have, all right? So that means that your B field right here is going downwards. Okay, so our B field is going downwards. That means that my B induced has to be in the opposite direction. So because I'm making a B field that is going downwards because its north pole has field lines coming out of it, the more field lines that come out of the north pole and goes inside this ring, the more of a B field you'll have, all right? And I'll recap it after I'm finished with this question, but right now, because we're making a B field going downwards, we're going to have an induced B field going upwards. So what direction is that? What direction is it? Well, I want you to put your thumb in the middle of this circle on the computer screen or wherever you're watching, and put your thumb going in the direction of the B induced, right? So the B induced is pointing upwards, so have your thumb pointing upwards as well, like you're making a good job sign, you know? And notice that your fingers are going to be pointing towards you. They're going to be curving towards you. And so my fingers should curve this way, right? And my thumb should be pointing that way, upwards. Okay, and notice that your your fingers are going to curve in a counterclockwise position. So for sure, we know that A is incorrect because that's a clockwise. We want a counterclockwise. That's a CCW, counterclockwise. All right, and C is incorrect, and E is incorrect as well because according to this equation, the charge multiplied by the velocity multiplied by the B field, which is the magnetic field, multiply that by the sine of theta equals a force. Well, we do have a velocity and our sine is 90 degrees. We're just going straight down. That's 90 degrees. And so because we're moving at a perpendicular angle and we have some charge and we have some velocity, for sure we're going to have a force, and that force is going to have us induce a current as well. So because we're moving a magnet towards a closed loop, we are going to have a force. We're going to have a current. If we were just standing still, if the magnet were not falling down but rather just staying in motion, or rather just being like a statue and not moving, then you would have no current. So answer choice E would be correct if this magnet were not moving, but we are moving, so we do have a current. So answer choice E is incorrect. All right. Okay, so moving on to the next part, and don't worry, I'm going to do a recap after this question is done because I think there's going to be a lot of questions on Faraday's law and Lenz's law, so we're just going to recap it afterwards. Alright, so we're going to redraw our loop or whatever. It doesn't have to be a perfect circle or anything. And now, like, let's say 3 seconds passed, and now our magnet is going to be over here. Okay, well, remember what I said about magnets, how we have things going into us? Well, you can say that this right here, we have field lines going towards the South Pole. Okay, so that means that there had to be field lines going here as well. And notice something. Notice that as we continue to go downwards, our velocity continues to go downwards, you're going to have less and less of a field line through the loop. So think of it in this way. We have field lines going towards the south pole of the magnet, but the further away that magnet becomes from the loop, the less field lines you'll have, right? So for instance, let's say that so like for a faucet at a sink, whenever you turn the faucet on, initially there's a lot of water, right? There's a lot of water coming out. That's a lot of field lines coming out of the faucet. But if we were to try to move away from that faucet and like try to make a path for the water to follow you, the water wouldn't be as much as, well, what I'm trying to say is at the beginning of the faucet, there's a lot of water. But when you move away from that faucet, the water is not going to be as plentiful. It's not going to be as fast. There's not a lot of water, right? And so when you move this magnet away from the ring, you're going to have less and less field lines. And so your B induced, your inducing current, is going to go downwards. Why? Well, the reason why we have a B induced going downwards is because we are decreasing the amount of field lines that are going into the loop. And whenever you decrease, you actually go in the same direction. So we go in same direction. And so notice that our magnet is going downwards, so our B induced is also going to go downwards. So what's going to be the direction? Well, the direction, you're going to put your thumb in the same direction as the B induced. And so if I have my thumb pointing downwards, notice that my fingers are going to be pointing away from me, and they're actually going to be pointing this way. And so my thumb is going to be pointing that way, my fingers are going to be pointing towards the left, and that's actually a clockwise motion. And so D would be correct. It's not always counterclockwise, as you see right there. Right here it would be counterclockwise and then clockwise. So when the magnet is above the loop, we're going to have field lines coming out of it. And so as we get closer and closer to this loop, we're going to have a bunch of field lines into this loop. We're going to have a bunch of field lines. The more field lines you have, the bigger that the magnetic flux is, right? And because the magnetic flux wants to oppose what's happening, we're not actually saying no to the change, we're just trying to oppose it, right? Because we're increasing the amount of field lines in this ring, we're going to go in the opposite direction. So notice that we were going down at first, so we're going to go in the opposite direction and point our fingers, our thumb going upwards, curl our fingers towards ourselves, and notice that it's going to be in a counterclockwise position. Okay, so let's say 2 seconds passed. Now our bar magnet is going to be below the ring, and we have field lines, these guys, pointing towards the south pole of the bar magnet. Now as the magnet falls away from the ring, you're going to be decreasing the flux. We're going to be decreasing the flux. And if we're decreasing the flux, we're going to try to oppose it. We're going to try to oppose the change. And because whenever we are decreasing, we're going to go in the same direction. So because my bar magnet was going downwards, my induced magnetic field, my B induced, is also going to be pointing in the down direction. So to say the direction, Lenz's law, right? You put your thumb in the same direction as the B induced, and then curl your fingers. And if you curl your fingers, you're actually going to notice that this is a clockwise fashion. That is a clockwise position. So now we have a flat coil consisting of 20 turns, and we have an area of 50 centimeters squared. And it's positioned perpendicularly. Okay, well, first of all, I'm going to stop myself and notice that perpendicularly, whatever that word is, I can't speak. That just means that our sine of, or it could be sine or cosine, but I know that this angle theta, that's going to be equal to 90 degrees. That's what a perpendicular is. So here's my force or whatever, and here's my surface. This angle right there is 90 degrees. Right? That's what perpendicular means. Okay. So now it's to a uniform magnetic field that increases its magnitude on a constant rate of 2 teslas to 6 teslas in 2 seconds. If the coil has a total resistance of 0.4 ohms, what is the magnitude of the induced current? And so over here, we're trying to solve what is the current. So what is our amps? Right here, as you can see from these answer choices. Okay, well, how do I do this? Well, they gave me my turns, and they gave me an area. They also gave me a change in the B field. So we can say that's delta B, right? That's delta B. And they also gave me a cosine. Is it cosine or sine? You know, I'm thinking about sine, right? Most likely. Of course, you're going to have a formula sheet, I hope, on the exam. And they gave me time. So I'm going to say that this is time. That looks pretty good. Well, like I said, this is the equation that you have to use. And notice that this is going to be equal to the EMF, which is just a weird looking E. But this E can also mean volts. And so it's not voltage per se, but for your case and for my case, we're going to call it volts, all right? obviously you're going to treat it the same way as a volt, alright? So don't be confused about what I'm about to do. Alright, so what is delta B? Well, delta B, delta just means final minus initial. So we're going to say final. We're going to say final B minus initial B. Alright, so what was my final B? Well, it says I went from 2 to 6. So my 6 is going to be the final minus the initial. So that's going to be 4 Teslas, right? And that happened in 2 seconds. Okay, so my time is going to be in 2 seconds. And what about the area? The area. Well, here is where you may have messed up when you were doing this problem. Whenever you have a centimeter squared, that's the same thing as saying centimeter times centimeter. Okay, and whenever you're doing these types of problems, you're going to have to go into the SI units. And SI units means that we're working with kilograms, meters, and seconds. Alright, so we don't have any kilograms, we don't have any mass, we don't have we do have seconds, that's good, but we don't have meters. So what do I have to do to get 50 centimeters squared to meters? Well, I'm going to have to convert 50 centimeters by 100 because there are 100 centimeters in a meter, and you're going to get 0.5 meters, right? 0.5 meters. Let's see, 50 divided by 100. Yeah, that's 0.5 meters. Okay, but notice that you only took out 1 centimeter. Because it was centimeters squared, you're going to have to divide 50 by 100 and then do it again. So 50 divided by 100 is 0.5. And then over here, you're going to say 0.5 meters divided by 100 is what? It's going to be 0.05. So yeah, don't mess up on that, right? Whenever you have a centimeter squared or centimeter cubed, you're gonna have to divide by 100 like 3 times or 2 times. In this case, we divided by 2 times, right? And so you may have gotten the same equation, right? But you may have forgotten to divide by 100 2 times. All right, so that's my area. That's my area. And of course, n is just going to be the amount of turns. So n is just equal to 20 turns. 20 turns. All right. So let's put this together. We have negative 20. The negative is just for sign, right? So you don't feel like confused if you get a negative sign. So negative 20, multiply that by 0.005, right? 0.005. And multiply that by the change of the B field, which is 4. Multiply that by sine of 90, but sine of 90 is just 1. Alright? And then divide that by the time that it took, and it took us 2 seconds. So when we put that into the calculator, and I'm going to put it right here, so that's negative 20, multiply that by 0.005, multiply that by 4, divide that by 2 seconds, you're going to get negative 2. You're going to get negative 2. Alright, but negative 2 what? Is it negative 2 current, negative 2 resistor, what? Well, we just solved for voltage. And so technically we have negative 2 or just 2 volts. Alright, now that we have our volts, what can we do to find current? Well, let's see here. They gave me the resistor and they gave me current, or they gave me voltage. So using Ohm's law, that the resistance, ohms, is equal to the voltage, or it could be EMF, divided by the I, the current. And so really, you have that the current is equal, notice that this little weird E is the same thing as saying V for voltage. So you can say that this little weird E, which we calculated to be the EMF, divided by the resistance is equal to the current. So we can say that 2 volts divided by 0.4 is equal to I. And if you were to put that into the calculator, you have that I is equal to half an amp, which is deadly, and you should probably not touch it. It'll kill you. And so right here, you would use, well, you wouldn't use it, but you would say that C is correct. This is half an amp. And we just use this equation, the number of turns multiplied by the area, multiply that by the difference of B, times the sine of theta, and divide all of that by the time in seconds. You're going to get your volts. After that, you can use Ohm's law, which says that the resistance is equal to the voltage divided by the current. The voltage is just another way to say EMF, right? We're going to be doing a lot of that in this practice exam, and you could just do some simple algebra to figure out what I is. But realize that whenever you have 50 centimeters squared, you're going to have to divide 50 by 100 2 times, all right? So that's really all you had to do for this problem. And just remember that whenever you have centimeters squared or cubed or quadrupled, whatever, you're going to have to divide 100 by this many times, right? Just remember that. All right, well, first of all, I just kind of want to just take care of some error right here. This is not an E. It should be a B, right? So we're going to say that is a B, right? And over here, the electric field is not a B, but rather it is an E, right? So in electron, so first of all, whenever it says an electron, you're going to be thinking that the charge, Q, is equal to 1.6 times 10 to the negative 19 coulombs, and that the mass is given to you, but the mass is going to be 9.11 times 10 to the negative 31 kilograms, right? That's what you should be thinking. Now we have a kinetic energy of K, which is 750 electron volts. Well, what's an electron volts? If you want to convert electron volts to joules, you should know that 1 EV is equal to 1.6 times 10 to the negative 19 joules. And hey, look at that. It's the same value. It's the same value. So whenever you say EV, you just multiply whatever you had, in this case 750, by the charge of an electron. And so if you want to figure out how much energy that is, you multiply it by 1.6 times 10 to the negative 19. So let's do that. 750, multiply that by 1.6 times 10 to the negative 19, and you end up getting that 750 electron volts turns out to be 1.2 times 10 to the negative 16 joules. Okay, cool. So we have that it is undeflected through a velocity filter containing an electric field and magnetic field. And it says that the velocity is perpendicular to the B field, and the velocity is perpendicular to the electric field, and the electric field is perpendicular to the B field. And frankly, that's a lot to know, and I don't know what any of that means, and you probably don't know either, so we're in the same boat. Let's just continue, right? If the magnetic field has a magnitude of 15 microteslas, or not micro, but milliteslas, what is the magnitude of the E field in the filter? So what is the magnitude of the E field? Okay, well, first of all, if I want to find magnitude, I'm going to have to do some weird stuff. So it says velocity, but I don't have my velocity over there. Why do I need velocity? Well, look, back in like chapter 20, you learned that the force is equal to the E field times the charge. And over here in chapter like 21, I think, or chapter 20, I don't know, you learned that the force is equal to the charge multiplied by the velocity times the B field times sine of theta. Okay, well, notice that we have a force and a force, and therefore we can set this guy equal to that guy. Alright, so let's set them equal to each other. So EQ, and notice that I only brought F is equal to EQ because that's really the only thing I know that relates force and the electric field. I'm not giving any distances. I'm not giving any point charges. So I'm not going to be using Coulomb's law. I'm not going to be doing that. I only have force, the electric field, and the charge. And so that's what I'm trying to do, you know? So EQ has to be equal to QV B sine theta. Well, it says that it was perpendicular, and so sine theta, that's just 1. So we're going to ignore sine theta. And notice that these Q values, the charge, are going to cancel. And so really, all I have is that the E field, which is what I'm trying to solve for, is equal to the velocity times the B field. Well, what's the problem? Well, the problem is that I do have the B field, it's 15 milliteslas, but I don't have the velocity. So what can I do? Well, the velocity, remember that work, right, is equal to the kinetic energy. Or you could just call it K. Alright, but the K was 750 electron volts, and we said it's 1.2 times 10 to the negative 16 joules. But what is work? Whenever you have mass, and it's explicitly telling you that, you should be saying, well, work, that's equal to 1/2 the mass times the velocity squared. And the work is also equal to the kinetic energy. And so you can say that 750 electron volts, or rather, we already converted it, but rather 1.2 times 10 to the negative 16 joules is equal to 1/2 mv squared. Now we have to solve for velocity. I can multiply this side by 2 times, right? And then divide by the mass, and then take the square root. And so we're going to divide by the mass. So we're going to have 2 times 1.2 times 10 negative 16. Divide this by the mass, and then take the square root, and that's equal to the velocity. So we're going to have this. We're going to have the square root. We're going to have the square root of 2 times 1.2 e negative 16, and then the mass of an electron, which is 9.11, times 10 to the negative 31, right? And so our velocity turns out to be 1.6 times 10 to the 7 meters per second. Okay, so that's the velocity. Now we have to multiply that by b. And so we're going to multiply this by b. So take your answer and multiply it by 15 e negative 3. And it turns out that this is around 244 kilovolts per meter. And it turns out that your answer should be C. So all you have to do was realize that an electron volt is 1.6 times 10 to the negative 19 coulombs, or joules, and realize that work is just 1/2 mv squared, and it's equal to the joules. You solve for your V and multiply it by the B fields to get your E. And the reason why we calculate using this equation is because it's an equation that relates to force and the electric field. And notice that the charge is going to be meaningless because the charge cancels out in the end. So if you had trouble doing that, just kind of rewatch what I did, and hopefully she's going to have the equation sheet so you don't have to remember the equations that I used, but hopefully it's going to be on the exam, right? Over here we have a conceptual problem. We have a solenoid that consists of 100 circular loops of a copper wire, and we have to find in which way the current is going to flow through the wire, right? When a current flows through the wire, notice that our directions are in the same direction. They're all going upwards. If we have a wire that has a current, and that current is going in the same direction, so we're going to say it's same direction, and that is equal to attractive. So it's going to be attractive. If it's going to go, if it is going to go in an opposite direction, let's call it oppo direction. Well, that is equal to repulsive. And because our wires aren't going in the same direction, A is going to be attracted to B, and B is going to be attracted to C. So you could say that A is attracted to B, and C is attracted to B, because they're going in the same direction, right? And, you know, if we had C going in the downwards direction, then the answer would be that A is attracted to B, B is attracted to A, but A is repulsed by C, and B is repulsed by C. So just keep in mind, if it's in the same direction, it's going to be attractive. If it's going to be in the opposite direction, it's going to be repulsive. And so E would be the correct answer. Now we have that an LC current has a capacitor and has a voltage of 5 volts. Okay, so V is equal to 5, and it has a capacitance equal to 20 picofarads. Pico is just negative 12. So times 10 to negative 12. That's a pico. And then it's left to oscillate. That means to kind of vibrate or shake around, right? We have to find the maximum value of the current. Okay, and then L, which is the inductance, it's given in henries, it's 10 to the negative 3 henries. Alright, so the main thing that you have to be on the lookout for here and on the exam is that whenever you want to find the maximum value for anything, for instance, let's say the maximum value of the voltage or the current or the resistance, well, you're going to be using the resonance frequency. So what's the resonance frequency? Normally you would just be using frequency, but in this case we're going to be using a very special spicy boy resonance. It's going to be F sub naught. So what is F sub naught? F sub naught, that's just equal to 2 pi, the square root of the inductance L times the capacitance, and then divide that spicy boy by 1. Okay, and that's the resonance frequency. And so whenever you have X sub L and you're going to have to use a frequency, you're going to be using this guy now, right? So we're going to actually get a number from this guy. So we're going to say 2 pi, multiply that by the square root of 10 times 10 to negative 3, and then multiply that by the capacitance, which is 20 times 10 to negative 12 picofarads, and then divide that guy by 1. So 1 divided by all that junk, and it turns out that your frequency, if I'm not mistaken, is a fairly large number. Pretty ugly too. It's around 3.5 times 10 to the, let's see, 3, 4, 5, so that's to the 5th, and let's call that hertz. Okay, so that's our frequency now. Okay, and let's work upwards. Alright, we have to find the maximum value of the current. So what equation am I going to use? Well, you can use this equation. You could do V RMS is equal to I RMS. And that could be equal to the X sub L, or it could be equal to X sub C. In this problem, we're just going to be using X sub L because I just feel like it, right? I just feel like it. And what's VRM? What is this? What is VRMS? Well, VRMS, that's just another fancy way to say V, and that's equal to I, and that's equal to V sub L, or X sub L, sorry, or chi. All right, but what is chi sub L? Well, chi sub L, that's equal to 2 pi, and normally it would be frequency, but notice that we calculated a frequency over here, so we're going to use this guy over here. Chi sub L multiplied by the inductance. Alright, so chi sub L is equal to 2 pi, and then the frequency that we calculated, it's 3.5 times 10 to the 5. Multiply that by the inductance of 10 times 10 to negative 3. Alright, so if you do that, we're going to have that chi sub L, chi is just a fancy way to say X. We're going to have 2 pi, multiply that by 3.5 e to the 5th, multiply that by 10 times 10 to the negative 3. It's around 22,000. Let's just say 23,000. Okay. So now we have chi sub L, and we can say that V divided by X sub L, just using this guy over here, well, that's equal to the current. Alright, so we have 5 volts divided by 22,000, and we end up getting 2.2 times 10 to the negative 4 amps. And of course, you can do this equation using X sub C, chi sub C, and you would get the same answer. And recall that chi sub C, that's just equal to 2 pi. Normally it's the frequency, but we're going to be using the resonance frequency right there, multiply by the capacitance, and then divide that by 1. So 1 divided by that guy, you're going to get chi sub C. And then 5 divided by that value is going to give you the same value of A. And so if you do chi sub C or chi sub L, they're going to be the same value, right? I just wanted to do the L one, so you don't have to take that L. I'm sorry, I couldn't help myself. I had to, take that joke. I've been waiting like 36 minutes to do that joke. Yeah, so the trick here was to realize that you have to use the resonance frequency right there. So now we have a particle with a positive charge of Q, a mass of m, and an initial speed of v sub naught. And it moves in a circular orbit of radius r in a uniform magnetic field of magnitude b. After completing one orbit, because it's lazy, how much work has been done on the particle by the field? Well, whenever it came to this one right here, me and the TA, yes, I worked this exam with the TA, so you're in safe hands. We said that in a circular loop right there, if you were to start over here, that's the starting line, and you were to stop in the same direction, let's call it the finish line, you're not going to do any work. So the answer is D. But why is it D? Why is it no work? Well, recall that work is equal to the force and its displacement. It's displacement, okay? So what's the difference between displacement and distance? Well, distance says that you could start at point A and you could travel over here and there and there and go over here to point A again, and we're going to be calculating the distance, right? And so let's say that distance was like 5 miles. So how much you traveled? Well, you traveled a distance of 5 miles. But what about displacement? Displacement says that you start at point A, and I don't care how far you go. You could travel the world. You could travel the galaxy. You could see the face of God. And if you still land at point A, technically your displacement is 0 because you started at A and you stopped at A in the end, and so you didn't have any displacement. You didn't have any net movement. You could travel a cajillion miles and have a 0 displacement. And so we started at A and we stopped at A, and so our displacement is 0. So the work is equal to the force times 0. Well, the work has to be equal to 0 because we stopped at point A and we started at point A and we stopped at point A, and that means that our displacement is 0, and a force multiplied by 0 is, guess what? 0. And so you had to graduate kindergarten school to really work with zeros. At least I did back in the day. It was like 2 years ago. And you realize that your displacement is not the same thing as distance. Displacement just cares about where you started and where you finish. Because we started in the same place and we finished at the same place, it's a displacement of 0. And so a displacement of 0 gives you a work of 0. So therefore, there was no work done on the particle by the field. So for question 7, it's not a really good one. Like, it's pretty easy to solve. It's just they didn't give you a picture. So I'm going to go over 2 case scenarios in case you see this on the exam. Let's say that you have a wire over here. Well, and that our wire has a current going this way, right? Because it's going in the positive x direction. So we're just going to say right here is our positive y, and over here is going to be our positive x. Okay, so we have a positive x current. That means it's going to the right. And let's say that we have a rectangle, right? And the rectangle is in the negative y direction. And let's say that it's moving. And because we're moving, for sure we're going to have a net induced field. Or I should say that in a better way. Okay, because we have a constant velocity, we are moving. And because we are moving, we are going to have an induced current. And that induced current is either clockwise or counterclockwise. If we were still, or if we didn't have a velocity, we would not have an induced current. Okay, but because we are moving, we are going to have an induced current. Okay, so automatically, because we're moving, it cannot be zero. All right, so now we're going to be using the right-hand rule for wires. I want you to get your pen or pencil, right, or stuffed animal, and put your thumb in the direction of the current. And for this wire, because it's going in the positive x direction, we're going to put our thumb pointing right. And so we're going to grab whatever we have and kind of like put your thumb in the x direction. Now your fingers should be pointing towards you over here. So your fingers should be pointing towards your eyes and then kind of go away from you. Okay, it's going to go away from you. So we have our fields going inwards to the page. That's what an x means. X just means inwards, period means outwards. So let's say that our field, or just to be a bit more obvious, in case you don't see it, and you know, I want you to have a good grade on this exam, so you know, I'm putting a lot of effort into doing this. Right, so let's say that our rectangle is going downwards. And so as we continue to go downwards, we're going to move away from this induced field. And since we're moving away from this field line, notice that this wire has, as a side note, this wire has field lines going this way, right? And so we are having a flux. These field lines produced by the wire are going into the rectangle. And as we move that rectangle away, we're going to have less and less field lines hitting us. If we have a decrease in magnetic flux, well, our opposition is going to try to oppose the decrease. And to oppose a decrease, to fight the decrease, I should say, we are going to go in the same direction. And because we're going to go in the same direction, we're not going to go downwards, I should say, but we're going to have the same value. We're going to have the same x. So we're going to go in the same direction, which is into the page. If I wanted to kind of like go against the grain, I would be periods. But because I'm pushing this rectangle away from the magnetic field lines, I'm going to be decreasing the flux. If I am decreasing the flux, I am going to be in the same direction. In this case, the direction of the magnetic field lines, which are decreasing, are x's. And to fight that decrease, I'm going to also be x's, okay? I'm also going to be x's to fight that decrease in flux. And so to find if you're clockwise or counterclockwise, put your thumb into the x's, right? So put your thumb outwards and then curl your fingers. And you'll notice that your fingers are going to curl like this, which is a clockwise position. That's a clockwise position. Okay, well, what happens if you had a wire over here, okay, and the wire had a current that was going to the right, okay, and then you had your rectangle right here, and we were still going downwards. All right, well, what happens? Well, again, you try to figure out where your field lines are going in your rectangle or in your wire. And so you put your thumb, you wrap your hand around the wire with your thumb pointing in the same direction as the arrow over here. This is your current. And then when your fingers are pointing at you, they're going to be periods. So we're going to have periods over here. And we're going to have X's in the bottom. Okay, so as that rectangle moves, it's going to have more periods inside the rectangle. And technically we are increasing the flux in that rectangle as we move closer and closer to the wire. Because we are increasing flux, I want to fight that change. I want to fight the change. So to fight an increase, we're going to go in the opposite direction. And so currently my direction is going to be periods. The opposite of periods is going to be X's. And therefore my flux is going to be X's now. Okay, so now again, figure out where your current is going to go. Put or I should say, your induced B field, put your thumb in the direction of the X, and then curl your fingers. And notice that you're still going to have a clockwise position. And so, for sure, I know it's going to be B, which is clockwise. Now we have to find out the resonant frequency for our RLC circuit, where we have a resistor of 10 ohms, capacitor 5 microfarads, and an inductance of 2 millihenries. Well, again, a resonant frequency, that's just equal to 2 pi, the square root of LC, and divide that. So 1 divided by 2 pi, square root LC. So again, that is 2 pi, and the square root of L, which is going to be 2 times 10, negative 3. Multiply that by 5 times 10, negative 6 microfarads, and divide that by 1. And if you were to do that on a calculator or in your head, you would get 1.592 kilohertz, not holts, but hertz. All right, so that was a give me problem. So now we have a primary winding of an electric train transformer. So my mom never let me play with trains. We couldn't afford it. But now I know how to make a transformer, and I could burn down the house to, get revenge. No, I'm joking. I'm joking. I would never do that. So now we have 400 turns, and the secondary has 50 turns. So okay, so whenever you're doing these types of problems, we have primary, and it's better for me to say the equation first. And I like to think of it as this. So we have IP. Okay, if we have IP, then we're gonna also have is. All right, so IP is, then we're gonna have, it could be volts or turns. In this case, I'm gonna do volts. We're gonna say that this is S, this is P. So notice that my P was upwards, now it's gonna go downstairs. And V is gonna be the same thing as N. So N is gonna go upstairs, and N is gonna go downstairs, NP. So V is the same thing as N, and VP is the same thing as NP. But the only thing that you should look out for is IP is, right? IP is wrong. So the little mnemonic, IP is opposite to VS VP. IP is opposite to VS VP. Okay, cool. So again, I wouldn't do that to my mom or parents. I was just being funny, okay? So the primary winding of an electric train transformer is 400 turns. Okay, so turns is N, and the secondary has 50 turns. Okay, so it looks like we're not going to be worried about current, so I'm just going to ignore this part right there. Okay, we have that this has to be equal to, let's see, 400 turns for the primary. Divide that by 50 turns. Oh, I'm sorry. So yeah, always look at what you're doing. So we have that the number of turns, right? That the number of turns is going to be, the primary is 400. So the secondary has to be 50. divide that by the primary of 400. So all I did was the 400 goes to the primary, which is P, and the 50 goes to the secondary. Alright, now the input voltage is 120 volts. What is the output voltage? And so really the input voltage is what you put into the system. The secondary is what comes out of the voltage. So whenever you put in your phone charger, you're putting in some amount of voltage, the input, and the output is going to be like 5 volts, 2 volts, etc. And so we're putting in, for the primary, 120 volts. And we want an output of some volts. And so all I have to do is just, this is the number, and it turns out to be, let's see, 5 divided by 40 is 0.125. So we have x of 120 is equal to 0.125. Now I can multiply this by 120. So multiply that by 125. And it turns out that x is equal to 15. So x is equal to 15 volts. For the for the 10th problem, it's just a give me. We have to find the direction of the magnetic force that's acting on the charge. Okay, well, we're dealing with a positive charge. And when I have a positive charge, I'm going to be putting my index finger in the direction of the velocity. And so my index finger is going to be pointing upwards. Okay, and then my middle finger is going to be pointing out away from me. So my middle finger is going to be pointing away from me. So it's going to be over there, right? And my thumb is going to give me my direction of the force. So my velocity was going upwards, my B field was going into the page, and I should be seeing an L shape with my right hand, right? Because this is how I do, point charges with the right hand rule. I don't use my actual hand, I just use my fingers. So my velocity is pointing upwards, my B field is going into the page, and my thumb is going to be showing me the direction. And so I should have a left direction, right, for the field, for the force. And notice that if my velocity were going upwards and my B field were going upwards, then they're going to be parallel and a force would not be acting on the charge. And so if you had a parallel force, then you're not going to have, if you have a parallel velocity and parallel B field, then you're not going to have a force. So it could be 180 degrees or it could be 0 degrees. You're not going to have a force. In this case, we have perpendicular forces, or perpendicular components, and so we do have a force, and that force is going to be towards the left. Now we have a triangle, which is just a spicy semi-rectangle, or whatever, semi-square, right? And we have a current of 12 amps and a magnetic field of 0.2 teslas. So now we have to find the magnetic force of F1 acting on the right side of the loop. So first of all, I kind of want to solve for that side, and that side, it's just L sub 1 plus L sub 2, and square that, takes the square root. You're going to get I, which is, or L sub 3. And so if you were to take 0.75 squared plus 0.75 squared, and then take the square root of that, it turns out that it would be around 1.06 meters. So that is 1.06 meters, okay? I just wanted to get that out the way. Right, so we have to find the magnetic force, F, acting on the right side of the loop. So when they're saying the right side of the loop, they're talking about this side, right there. Okay, that's cool. So what equation am I going to be using? Well, they just gave me the length, the current, and the B field. And they gave me the sign. Yeah, it's not obviously explained to you, but the sign, the theta, is just going to be 90. Because again, this is a 90-degree angle. We are perpendicular, and sine of 90 is just 1, so I'm not going to write it out. So the force, the equation, should be the amps times the length times the B field, okay? Right, so we have a force, and that's equal to 12 amps multiplied by 0.75 meters, multiply that by 0.2 Teslas. And so the force is equal to about 1.8 newtons. Okay, now we have to figure out the magnetic force F2 acting on the bottom side of the loop. Well, notice that we have a B field going to the right, and our loop is going to the left. And these two guys, they're parallel. And what did I tell you just like 50 minutes ago about parallel field lines and currents? Well, if you're parallel, then your sign is going to be 0. You don't have a degree, right? You don't have any angles. And sine of 0 is just equal to 0. So let's see here. Mathematically, you can say that we have a current, we have a length, we have a B field, but our sign is 0 degrees. And because we are 0 degrees, is going to be that F is equal to 0 newtons. This is only possible because we have the B field going in a straight line in the x component, and this guy only has x components, if you like to think of it in vectors. But because we are going parallel, or rather anti-parallel, we're going to have an angle of 0, and sine of 0 is just 0. So the force is 0 newtons. Okay, now we have to figure out the magnetic field, the magnetic force F3 acting on the left side of the loop, this one. And well, it's not too bad, but before I get into it, I want to tell you something very, very important. And me and the TA discussed this. Also, pay attention to how these free response questions are being answered and how I'm thinking about what I'm doing, right? Because most likely the professor is going to put these exact same free responses, maybe one of them, on the exam. And I don't know which one it's going to be, but pay attention to what I'm doing and you'll be fine. So it's important for you to know on this problem that we are not going to have an x component for the hypotenuse. Why? Well, notice that we are going at an angle. That angle is going to be like 45 degrees, okay? Because that's 45 degrees. A triangle always wants an interior angle of 180 degrees. 45 plus 45 is 90. 90 plus 90 degrees is 180, so that's good. But notice that my y component is going to be going upwards, that's good, but my x component is going to go this direction. And you see the problem there? The x direction is in the same direction of that B field. Whoa, dude, for real. So because that x component is in the same direction as that B field component, it's going to cancel out. It's going to be 0. But the y component, the red one, is not parallel to the B field. Actually, it's perpendicular to the B field. Wow, okay. So we're perpendicular to that B field. And it's going to occur at every segment for this wire. So over here, it's going to have a y component that's going upwards, and it's going to have an x component. We can do this into infinity, covering this whole wire, this whole hypotenuse. You're still going to have that the x's cancel out, but the y components do not cancel out. And so we can say that the force, that's equal to the amps times the length, which we said was 1.06, multiplied by the B field, and then multiply that by sine. And notice that it's not a 90-degree angle anymore. We're actually at some angle. And we said that that angle is going to be sine of 45 degrees. So it's going to be sine of 45 degrees. Okay, well that means that we have 12 times 1.06, multiply that by 0.2, multiply that by sine of 45 degrees. And it turns out that F is about, let's calculate it. We have 12 times 1.06, multiply that by 0.2, multiply that by sine of 45 degrees. Turns out to be around 1.8, that's an F. Turns out to be 1.8 newtons. So remember that you don't have an x component for the hypotenuse because the x component is parallel to the x, or parallel to the B field right there. But you do have a y component, so you just put sine of 45 degrees, right? And you'll be fine. All right. Before I get into this, I kind of want to just name these guys. I want to name them. I'm going to call this one beta because this problem gets really ugly really quickly, and we're just going to take our time. We're going to call this one, let's call that mu. If I can draw it out, that would be nice. Hold on. There it goes. Okay, so it took me around 3 minutes to draw that. That's very nice. Let's call that mu, and it's not mu sub naught. Let's call that mu. Okay, and let's call this one alpha. Right. And let's do that in a different color. So the reason why I did this is because it gets pretty bad if you're not keeping in track. So first of all, we have to find the magnitude of the total magnetic field at the origin, which is this guy, B total, due to the 3 wires. What is the magnitude of each wire? So we have to draw the magnetic field for each wire, and then calculate the x and y components, and then combine them together to get the B total. So in my opinion, this is like one of the hardest ones of the free response questions. So I'm going to take my time, and if you're annoyed, maybe increase the speed by 2 times, right? So whenever I have the B field, I'm actually going to put my thumb in the direction of the B field. And the reason why I'm doing this is because I want to actually map out the field. And so let's make sure that this is in the same color. So my thumb for beta is going to be pointing towards me, okay? And then I'm going to curl my fingers around. Okay? And notice that my fingers are going to go in this direction, a counterclockwise direction, right? And we're going to make our field lines, if we have this question on the exam, separate your pictures into different lines. And so this one is going to have kind of like dashes, and we want to go through the origin. And over here we have, remember that our for beta, the current was going this way, okay? So that means that over here we have a current right there. And let's say in the ideal case, we have a current that only goes upwards. So let's say that because we're going in a counterclockwise direction, the moment that we pass through the origin, our current is only going to have a y component. It's only going to have a y component. So let's make that explicit. Beta has a y component, not an x component, but a y component. Okay, that's cool. Now for what about alpha? Well, alpha is going to go into the page. And so I'm going to put my thumb into the page and then twist my fingers. And notice that if I twist my fingers, my field is going to go that way. It's going to go in a clockwise direction. Okay. And let's actually make that into a solid line. So we go over here. As we pass through the origin, we are also going to have a y component. So this one also has a y component the moment we pass into the origin. So I don't care about this segment right here. I don't care. All I care about is the origin, right? Now, what about for mu? Well, mu is going to have the B field going out of the page. And so my thumb is going to be pointing out towards me. We're going to curl our fingers going in the counterclockwise direction. It's going to go in the counterclockwise direction. Okay. So because this happens, we're going to go over here. And then we're going to hit the origin. And, I shouldn't be drawing it in that color. I should be drawing it in the pink color. And we're going to say that this is kind of like a, these are going to be dots. So we have our dots going this way. And notice that we don't have anything going over here. Nothing goes on over there. But we do have something going on in the x component. And so my x component is going to be right there. So mu only has something going in the x component. And so this is pretty nice, isn't it? We realize that beta and alpha, they go in, beta goes in a counterclockwise direction, alpha goes in a clockwise direction, but they're going to meet up in the origin, and they're going to go in the y direction. Only in the y direction. There's no x direction over here. Yeah, there's an x direction over here, but as soon as we turn that corner, there's no more x. There's only y over there. That's for beta and alpha. But for mu, we're not going to have any y components over here. Instead, we're going to turn that corner right here, and that corner is going to give us our x components. So mu has an x component, beta and alpha only have y components. So that's good. We're going to say in a different color, we're going to say in black that, that beta sub y plus alpha sub y, right? Well, we're going to call that b sub y. And then mu sub x is going to be b sub x. Afterwards, we can say that the b total, well, that's just equal to the square root of b sub x squared plus b sub y squared. And so all we have to do is just find the beta. All right, so how do I find beta? Or just the B field? Well, they gave me my amps, they gave me my distance, and they gave me the sine. Okay, they gave me the sine, or the angle, right? Well, I can use that beta, or that B, is equal to mu sub naught multiplied by the amps divided by 2 pi distance. And sometimes we're not going to have the pi. Sometimes we're just going to have 2D or 2R. That occurs in solenoids usually. But for this case, we're not working with solenoids, so we're just going to use a vanilla 2 pi D. Okay? Yeah, so we have our amps, and mu sub naught is just a constant. Mu sub naught is just equal to 4 pi. Don't forget your pi, seriously. Times 10 to negative 7. And I'm not going to show units because, frankly, that's really confusing to people, and it's confusing to me. I think Einstein had troubles with units. He didn't talk until he was like 4, so he probably did have issues. But we're not going to include units. We're just going to put 4 pi times 10 to negative 7 for mu sub naught. Okay, but what's my distance? Oh man, what's my distance? Well, here's what comes into play. We have our theta, and that's going to be a 30-degree angle. That's a 30-degree angle. And then our d, the distance, is going to be 2 meters. That's going to be 2 meters as well. Okay. But what about this? Because in an ideal case, I want to solve for all my missing sides, right? So let's try to figure out what it is. Let's see. We have that sine of theta that's equal to what? So that's opposite over hypotenuse. If you remember, you put so, and then ka, and then toa. So that's really just sine is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So this would be adjacent. This would be opposite. This is going to be hypotenuse relative to this theta. Okay? And really, that's an h. Anyways. So in this case, I'm trying to solve for x right there. So we're going to say that sine of 30 degrees is equal to x divided by h. Turns out that h is 2 meters, and to solve for x, we could just multiply this by 2. So 2 times the sine of 30 degrees, it turns out to be 1. And that's a disappointment. I thought it was going to be something spectacular, but it's going to be 1. That's going to be 1 right there. And then you can solve for this side using Pythagorean theorem or something else. I'd rather solve using the trig identity. It just saves time. So we're going to be using that cosine of 30 degrees is equal to what? The adjacent, which is x. We're trying to solve for this part now. X over the hypotenuse, which turns out to be 2. And so if you multiply this side by 2, you get x. So let's see, 2 times the cosine of 30 degrees turns out to be 1.73. So x is equal to 1.73. X is equal to 1.73. And now let's erase everything that we did. Just to save space right there. I hope this is helping you. Yeah. Because this is not fun. I mean, it's kind of fun, but it's not really that fun. But anyways. So where was I? Yeah, so now we found out our distances. And we can solve for b now. So what's the b for beta? Well, beta, that's just going to be mu sub naught, which is 4 pi times 10 negative 7. Multiply that by the amp, which is 4.8. Divide that by 2 pi. And then the distance. So the distance from here to the origin, that's going to be 1.73. Right? So that's 1.73. And if you do that, you actually get 5.54 times 10 to the negative 7 Teslas. Alright? Now what about for alpha y? So for alpha y, it turns out that you're going to have 4 pi times 10 to the negative 7. That's mu sub naught. We're going to multiply that by the amps, which is 4.8. Divide that by 2 pi of, what's the distance over here? Well, the distance is going to be the same thing. It's going to be 1.73. This is also 1. Alright, so that's 1.73. We just calculated it. It turns out to be 5.54 times 10 to the negative 7 Teslas. Alright. But what about mu sub x? Well, mu sub x, it turns out that it's going to be 4 pi times 10 to the negative 7. Multiply that by 4.8. Divide that by 2 pi. And the distance from this guy to that guy turns out to just be 1 meter. So it's going to be 1 meter. And that is equal to, I believe it's 9.6 times 10 to negative 7 Teslas. Okay, so now we just have to add beta sub y and then alpha sub y together. So we're going to be adding them together. So let's see. 5.54 times 10 to the negative 7 plus 5.54 times 10 to the negative 7. If you were to add these together, you would get 1.1 times 10 to the negative 6 Teslas, right? Okay. Oh, it's a very tedious problem, but it's good. So now we have mu sub x squared plus by squared. This is by. So now we have square root of 9.6 times 10 negative 7 squared plus 1.1 times 10 negative 6 squared. And if you do that, you end up getting 1.46 times 10 to the negative 6 Teslas. Awesome. So that was your answer. I just took my time explaining it to you. Hopefully you could just replay it and solve it for yourself. But now we have to solve for part B. What is the direction of the net force of mu sub x? That's what it means by 1 meter on top of the wire. It's just referring to this guy, that's 1 meter. And frankly, that is true because we said that this is 1 meter over there. Okay, so what is the direction of the force due to the other two wires? Well, very simple. So mu sub x is going in the same direction as beta sub y. Notice that they're both coming out towards me. Because they're in the same direction, mu sub x is going to be very attracted to beta sub y. And so we're going to have a net force, well, not a net force, but a force going downwards to the right or to the left of beta sub y. Okay, now notice that mu sub y and alpha sub, notice that mu sub x and alpha sub y, they're going to go in opposite directions. So mu sub x is going out towards me, but alpha sub y is going into the page. Because they're going into the page, they're going to go and be repulsive. Because think of wires. if a wire is carrying the current in the same direction as the other wire, they're going to be very attractive. But if they're carrying currents in the opposite directions, they're going to be very repulsive. Because beta is in the same direction as mu, they're going to be attractive. And so mu is going to go towards beta. The reason why we're not putting an arrow from beta to mu is because we're saying what is the force on mu sub x, on the 1 meter, on the 1 meter component. So this is the 1 meter component. So it's 1 meter above the origin. So we're only caring about mu right now. So mu is going to be attracted to beta, but since mu is in the opposite direction as alpha, they're going to be repulsive. And so mu is going to be repulsive to alpha. And if you were to complete the circuit, or not the circuit, but the picture, you would have a force going to the negative x direction. So the negative x direction right there. If you can't see that, you have something over here, right there. Complete the square. It's kind of like that. Complete the square. It goes right there, okay? In the negative x direction. That's called the parallelogram method. If you can't see that, we have a force going this way, we have a force going that way. Complete the square. Where's the fourth vector, right? Vertice or whatever. Well, if you complete the square, you're going to have the fourth corner right here in the negative x direction. Now, what happens if the bar slides down? What is going to be the direction of the current? Well, when the bar slides down, this is the bar right there. If it slides down, you're going to be exposing more area of the circuit to the B field. The more area you have being exposed to the B field, the more magnetic flux you'll have. Now, I'll ask you, do we want a magnetic flux? Do we want an increase in the magnetic flux, or do we want to change a magnetic flux? Well, you don't want to change a magnetic flux, right? And so whatever change that does happen, we want to oppose it. Because we're increasing the area as we go down, right? Let's say that this is a candy bar right here, and this is the foil right here. The more foil you remove, the more of the chocolate bar that you're exposing. And so we don't really want our chocolate bar to be exposed to the air around us. The air is going to be acting as our magnetic field. And so because I'm exposing more chocolate from my chocolate bar as I remove the foil, as my bar goes down, there's more air being exposed to the chocolate bar. And so I don't want to expose my chocolate bar to the air, aka magnetic field, right? So as I remove this foil from my chocolate bar, there's going to be a lot more flux, a lot more magnetic flux, or a lot more air touching the chocolate bar. And because I don't want to have flux touching my circuit, I'm going to oppose the direction. So to make a long story short, because we're increasing the area, right, we're going to be increasing the magnetic flux. And because we don't want an increase in magnetic flux, we're going to have to go in the opposite direction. So right now my direction is going to be x's. And because I don't want to have x's, I'm going to go in this opposite direction. I'm going to say that this is going to be periods. And so what direction is my flux going to be? My induced current? Well, I put my thumb in the direction of the periods, and I'm going to curl my fingers. And it turns out that my fingers, when they curl, they're going to go in the counterclockwise position. And, professor already showed you the answer. So for sure, the current is going to go towards the right. And so you could say that it's going to go in the right side, going in a counterclockwise direction, right? Also, you can just do the right-hand rule, and you can say that because my velocity is going downwards, so I'm going to put my finger downwards, and then my middle finger is going to go into the page because my x's, so we're going to have a middle finger going that way. So my finger is going downwards, my middle finger is going into the page. We're going to say that the right hand, my thumb, is going to go left, which is true. So it's going to go in the right direction. Okay. So now we have to figure out what speed will the bar experience no net force. Okay, so I don't have enough room for B down here, so I'm just going to move it over here. Okay. Well, we have to figure out how to do this. Right. So to do question B, you're going to have to realize that we're working with gravity. And look, mg, remember that in mechanics, which is physics 1, that force is equal to the mass times acceleration. Well, acceleration in this case, that's just equal to gravity. And remember that gravity is around 9.81 times 10, or not times 10, but rather meters per second squared. Okay? So F is equal to mg. Okay? That's cool. But I want to have my force relating to some sort of velocity, right? Some sort of velocity. Well, I don't know how to do that yet. So what relates length, the B field, and velocity? How do I get that? Well, I have my length and I have a B field. And the only equation that gives me velocity with that would be, no pun intended, it would be that, E, which is just going to be voltage. Remember that this is just volts. That's equal to the amps, right? Or not the amps, but rather the voltage multiplied by, I'm really sorry, not the voltage, but the velocity, V sub naught, that's velocity, multiplied by the B field, multiply that by the length. Okay, cool. So how do I relate that to force? Yeah, it's a really bad equation, a really bad problem. It's not very intuitive, I guess. But listen, I'm just going to be spitballing right here. I'm just going to be kind of pulling out some equations. Well, remember that I have my current. Well, I don't have a current, but I have a length and I have a B field. Alright, if I have a B field and length and I have forces, well, what I'm going to be doing is that I'm going to say that the force is equal to the amps times the length times B, right? That's the force of a wire. Well, we have a force and we also have a force. So maybe we can set that equal to each other, right? Well, if we did that, we have that mg is equal to ILB. Okay? Well, that doesn't really do much for us. But now we have to bring in, this is why I don't like this problem, we have to bring in a different equation. Well, in Ohm's law, we have that the resistance is equal to the voltage, we'll say that's E, right, whatever that is, and I. And so if I solve for I, we have that I is equal to epsilon over R, right? Or rather, we could say that epsilon, since I want to relate all the equations together because it's a really dumb question, you could say that resistance times I is equal to epsilon. Okay, hey, we're getting somewhere. We're getting somewhere. Do you see what I can do? I can solve for I and then set I equal to each other, right? Okay, so R times I is equal to E, the voltage. That means that R times I is equal to this guy, VBL. Okay, well, I have I over here and I have I over there, so let's solve for I. We have that I has to be equal to VBL divided by R. Okay? And solving for I over here, we have that I has to be equal to mg divided by LB. Okay. So now we're going to set i's equal to each other. So mg over LB is equal to VBL over R. Solve for V. Well, if we solve for V, we have that RMG over LB divided by LB, so times LB. So that'll give us R. Really, this is just LB squared, and it's not R, it's going to be V. So this is going to be 0.01, multiply that by the mass of 0.5, multiply that by 9.81, divide that by the length of 0.5 times the B field of 0.2, then square that, you end up getting a value of 4.9 meters squared, or not meters squared, but just meters per second. Whew. Okay, so it's not very obvious, but let's recap. So notice I had a mass and a gravity, and it's going downwards. I remember that mass is equal to ma. In this case, acceleration is going to be gravity. So mass, or force, is equal to mass times gravity. Okay, now I'm working with wires, so I'm going to have that force is equal to the amps times the length times the B field. Well, I could set F equal to this F and have that mg is equal to ILB. Okay, but I just have, just a mass right now, but I remember that I have velocity, I have a B field, and I have a length. So those are my recipe for the E, the EMF, which is the voltage. And we could say that EMF is just equal to velocity times B times L. But then I remember that EMF is the same thing as voltage, and in Ohm's law, it says that the resistance is equal to the EMF divided by the amps. If I solve for EMF, I have that resistance times amps is equal to EMF. So it's equal to this guy. So we could say that R times I is equal to VLB, and I'm trying to solve for my velocity, V sub naught. Okay, but notice that I have something in common. I have the amps right here and an amps right there. So if I solve for amps, I could relate them to each other. So solving for amps, I had that I is equal to velocity times the B field times the length divided by the resistance. Okay, now I have I over here. I'm going to solve for I using this equation. Solving for I, we have that I is equal to mg divided by LB. And because we have two i's, we can set them equal to each other. So mg divided by LB is equal to VBL divided by R. And because we set them equal to each other, we can solve for the unknown, which is velocity. And so you really have to use 4 equations to solve this problem. Not fun, not good, but now if it's on the exam, you know how to solve for it, you're going to do amazing. We are now dealing with an LCR circuit, and it gives us that the inductance is 25 millihenries, the capacitance is 25 microfarads, and the resistance is going to be 20 ohms. The maximum potential is 300 volts, and the angular velocity is just going to be 2,000 radians per second. Right? What is the total impedance of the circuit? Well, total impedance, you can say that Z is equal to the square root of the resistance, which they give you, squared, plus, now I like to think of it in this way, X sub L, L's for lead, X sub L leads X sub C. And you square that. And so that's the impedance. So we can already find the impedance. What is X sub L? Well, X sub L, you can think of it as omega times the L right there. And if you don't have omega, we do have omega, but if you don't, omega, that's just equal to 2 pi times the frequency, right? But in this case, we do have omega. So X sub L, that's equal to 2,000. Multiply that by 25 times 10 to the negative 3 henries. And X sub L is going to give you 50. Okay. Now, what about X sub C? So X sub C, that's equal to 2 pi times the frequency times the capacitance divided by 1. But 2 pi F, that's just omega. And so really it's just going to be that x sub c is equal to omega times L, or not L, but rather C divided by 1. And so that becomes 2000 times 25 times 10 to the negative 6, that's what micro is, over 1, which turns out to be 20, right? Okay, so now x sub L minus 20 minus, x sub C, that turns out to be 50 minus 20, which is 30. Now, 30 squared is about, it's a very large number. So 30 squared is 900. Okay. And the resistance, we said it was 20. And so Z, that's just equal to, 20 squared plus 900. So the resistance is going to be 20 squared, which is 400, I think, plus 900. And it's going to be about like 36.055. So that is equal to 36.055 right there. Pretty good. Let's erase all this really quickly. Okay. Now we have to find what is the maximum current. What is the maximum current that is going through here? Well, the maximum current, you would have to use the okay, so before we get into that, what did we solve over here? Well, right here, that's going to be like the maximum resistance. So you can say that this is R max, right? And now this is asking for current. Okay, well, we can use Ohm's law. We can say that R max is equal to V max. This is actually V max divided by I max in 3D, So if we want to solve for I max, then we would have V max, that's M, divided by R max. And so I max would have to be equal to 300 volts over here, divided by what we just solved for, the impedance is going to be 36.055, and it turns out to be 8.33 repeating. That's what the bar means. It just means repeating. And so that's amps max. Okay. What is the maximum voltage across each circuit element? So what it means by circuit element is that for an LCR current, this is an element, that is an element, and that is an element as well. And notice that this is in series. And so in series, the voltage is not constant. Voltage fluctuates between each element. So we're going to have to figure out which one we have to solve for. So for L, we can use that V max is equal to I max, multiply that by X sub L. Okay, but X sub L, that's just really omega times L, right? And we're trying to find the maximum voltage. Well, V max, that turns out to be 8.33 times omega sub L, not omega sub L, well, omega times L, that's 2000 times 25 millihenries. Turns out we already solved for that. That's going to be 50. So this is just 50, right? That's X sub L. And that gives us a voltage of 416. Now, that's for X sub L. For X sub C, we can say that V max is equal to I max times x sub c. Turns out that x sub c is just really omega times capacitance over 1, or divided by 1. But again, we already saw for this one, we said that it was 20. Okay, so we can say that Vmax is equal to 8.33 times 20. That gives us 167 volts for x sub c. And then finally, for the resistance, we can just use Ohm's law, which says that R is equal to V over I. Solving for V, we can say that R times I is equal to V. And so Vmax is equal to R max, or just the resistance, right? So we could say that I max, which is 8.33, multiply that by 20 ohms. And the Vmax, that's just equal to 167. And so that's how you do that problem. I hope that you do well on your exam. I hope that this video kind of showed you how to think about these questions. Most likely one of these free responses is going to be on the exam. I'm not saying that it will be, but one of them at least is going to be on the exam. And now you know how to work each one of them. You're going to rewatch this video and you're going to do amazing. Remember that I believe in you, and I just hope that you do well on your exam. Thank you for watching this video. I hope that you have a great day, and I hope that you continue to learn. So thank you for watching, and just have a great day. Thank you.